Chapter 6.2, Dot Products of Vectors. This will correspond with Learning Target 8.2. Dot product. Vectors can be multiplied in two different ways. We can take a cross product that gives you a vector that's perpendicular to the plane of the two vectors being multiplied. We will be looking at this at a later chapter. What we're looking at in this chapter is the dot product. The dot product will give you a scalar, which is a number, not a vector. To find the dot product of two vectors, you multiply the corresponding components and add them together. So the dot product of vector u and vector v is u1 times v1 plus u2 times v2. To find the dot product of the vector 4, 3 and the vector -1, -2, we multiply 4 times -1 plus 3 times -2, and we get the scalar -10. Try these. Find the dot product of the given vectors. Properties of dot products. If u, v, and w are vectors and c is a scalar, the dot product of u and v is the same as the dot product of v and u. The dot product of u and u is the same as the magnitude of u squared. 0, the dot product of 0 and u is 0. Number 4 tells us that the distributive property works, and number 5 tells us that the associative property with vectors and scalars also works. One of the uses of dot products is to find the angle between two vectors. If theta is the angle between the non-zero vectors u and v, then cosine theta is the dot product of u and v divided by the magnitude of u times the magnitude of v. So to find theta, we take the arc cosine of all that. In the next slides, I'll show you how to apply that. Finding the angle between vectors. If vector u is -2, 3, and vector v is -4, -1, we want to find the angle between the vectors u and v. We'll call that angle theta. Taking our formula, where cosine theta is the dot product of u times v divided by the magnitude of u times the magnitude of v, we then insert the numbers from our vectors. The dot product of u and v is -2 times -4 plus 3 times -1, and the magnitude of u is the square root of -2 squared plus 3 squared, and the magnitude of v is the square root of -4 squared plus -1 squared. In the numerator, we then get 8 minus 3. In the denominator, we get the square root of 13 times the square root of 17, which gives us 5 over the square root of 13 times the square root of 17. Putting that into our calculators, we get cosine theta is approximately 0.336, and I rounded it here. You should leave it unrounded in your calculator as long as possible. And taking the arc cosine of 0.336, we get approximately 70.3 degrees. And looking back at the diagram, we can see here theta is approximately 70.3 degrees. Try this. Find the angles between vectors u and v if vector u is 5, 2 and vector v is -6, -1. Work it out and bring it into class. Moving on to the next concept. If vectors u and v are perpendicular, then the angle between them, by definition, is 90 degrees. If we take that information and put it into the formula for the angle between vectors, we get cosine 90 degrees equals the dot product of u times v divided by the magnitude of u times the magnitude of v. Think back to the unit circle. What is the cosine of 90 degrees? The cosine of 90 degrees is 0. So putting that into the equation, we get 0 equals all that information. Multiplying both sides by the magnitude of u times the magnitude of v, we get 0 equals the dot product of u and v. Now remember, we started with the concept that u and v are perpendicular. So when they're perpendicular, the dot product is 0. Orthogonal. The term orthogonal and perpendicular mean almost the same thing. The only difference is dealing with the 0 vector, which has no direction angle. So technically speaking, the 0 vector is not perpendicular to any vector. However, the 0 vector is orthogonal to every vector. So except for this special case, orthogonal and perpendicular are the same. So the vectors u and v are orthogonal if and only if the dot product of u and v is 0. Proving that vectors are orthogonal. To prove that they're orthogonal, all you have to do is show that their dot product is 0. Work this out and bring it into class. Our next concept is projecting one vector onto another. One of the uses of dot products is to find the projection of one vector onto another vector. What this means is if we take a perpendicular line dropped from the head of vector w onto vector v, this is called projecting vector w onto vector v. And here's the mathematical formula. Assuming that u and v are non-zero vectors, the projection of u onto v is the dot product of u and v divided by the magnitude of v squared, and all of that is multiplied by the vector v. And now we'll apply it. We're going to find the projection of vector u, which is 3, -7, onto vector v, which is -2, -6. Looking again at the formula and plugging the numbers from the vectors into it. On the top, we get the dot product, 3 times -2 plus -7 times -6. And on the bottom, the magnitude of v squared is the square root of -2 squared plus -6 squared. All of that is squared. And then we multiply it by the vector -2, -6. Calculating that, we get 36 over 40 times the vector -2, -6. Reducing our fraction, we get 9/10 times the vector -2, -6. 9/10 is our scalar times our vector -2, -6. So we multiply 9/10 times each component. We get 9/10 times -2 and 9/10 times -6. Multiplying our fractions, we get -18/10 and -54/10. And dividing, we get the projection of u onto v is the vector -1.8, -5.4. We can take this information one step further. We have projected one vector onto another vector. We can now write the original vector as the sum of two orthogonal vectors. In this diagram, vector w is projected onto vector v. The projection is vector xu. We can rewrite vector w as xu plus uw. So returning to our earlier problem, we found that the vector projection of u 3, -7 onto v -2, -6 to be -1.8, negative 5.4. If we want to write u as the sum of two orthogonal projections, we subtract the projection from our original vector u. So we get the vector 3, negative 7 minus the vector negative 1.8, negative 5.4 equals the vector 4.8, negative 1.6. The vector u can now be rewritten as the projection of u onto v, which was negative 1.8, negative 5.4, plus the vector 4.8, negative 1.6. Because when we add those two vectors together, we get our original vector u, which was 3, negative 7. Now let's see if you could put all of this together. Find the vector projection of u onto v, then write u as the sum of two orthogonal vectors, one of which is the projection of u onto v. The vector u is negative 2, 8, and v is negative 9, negative 3. Work this out and bring it into class. And now for your entertainment, we have another great deal for you. See you in class.